Let's start out with the initial situation. Let's imagine M1 is 6 kilograms and M2 is 4 kilograms. V1 initial is 8 meters per second and V2 initial is 3 meters per second. So we notice that V1 is moving faster than V2. It's going to catch up and they're going to collide. So yes, we are going to have a collision, we assume. Now typically I am very, very careful about significant figures, but let's just imagine that we've got exact numbers here. I don't want to constantly be worrying about adding in a 0.00 or something like that. So let's just imagine that we've got exact values here, and I'm not going to worry about keeping track of sig figs just for the moment, just to make the calculations go a little bit faster. All right, let's take a look. What is the total initial momentum? P initial. That's going to be M1 V1 initial, in other words, 6 kilograms times 8 meters per second, and then plus M2 V2 initial, so that's going to be 4 kilograms times 3 meters per second. And what's that give us? Well, we've got 6 times 8, that's 48. 48 kilogram meters per second, plus 4 times 3, that is 12 kilogram meters per second, which gives us a total of 48 plus 12, or 60 kilogram meters per second. So that is our total initial momentum. Let's keep in mind that the total initial momentum is also equal to the total mass times the velocity of the center of mass. So we can use this to determine what the velocity of the center of mass is. In other words, the velocity of the center of mass will be the total initial momentum divided by the total mass. Let's just for the moment say that this is the initial velocity for the center of mass, okay? I'll say why, we're just going to say it for the moment anyways. So the initial velocity for the center of mass then, initially, will be equal to the initial total momentum, which is 60 kilogram meters per second, divided by the total mass. Well, what's the total mass? We've got 6 kilograms and 4 kilograms, so the total mass is 10 kilograms. So we divide by 10 kilograms, and what do we get? We get 6 meters per second. So that is the velocity of the center of mass. So what does that mean? As these objects have some initial position, we're going to have some center of mass that will be closer to the 6 kilogram mass than the 4. But as the masses move, that center of mass is going to be moving along with it. So that center of mass, we know, is moving to the right, because this is positive, at 6 meters per second. Okay, good. Now, what is the kinetic energy initially? I'm going to write this over here, but then we'll just put all of our results over on this side, and so that we'll have space to do the final situation over there. So what is our initial kinetic energy? The initial kinetic energy will be the initial kinetic energy of the first mass plus the kinetic energy of the second mass. So what do we get? We get 1/2 times 6 kilograms times 8 meters per second squared plus 1/2 times 4 kilograms times 3 meters per second squared, which is 1/2 times 6 times 8 squared, that is 192 kilogram meters squared per second squared, that's a joule, plus 1/2 times 4 times 3 squared, and that is 18. So the total kinetic energy is 192 plus 18, or 210 joules. That is our total initial kinetic energy, the sum of the kinetic energies of both objects. But what I want to do is take a look at one more thing. I want to look at what is the kinetic energy of the motion of the center of mass. So thinking of the entire system in terms of the motion of its center of mass, let's figure out what that is. That's going to be 1/2 times the total mass times the velocity of the center of mass squared, and we're going to use the initial velocity of the center of mass, so this will be the initial kinetic energy of the center of mass. And what do we get? We get 1/2 times the total mass, which is 10 kilograms, as we saw, 6 plus 4, times the velocity of the center of mass. The velocity of the center of mass we found to be 6 meters per second. So 6 meters per second squared. Multiply that out, and what do we get? We get 180 joules. All right, so what is this telling us? Our system as a whole, if we kind of follow along just the center of mass, that accounts for 180 joules of the total kinetic energy. There is some extra in there, because that doesn't account for all the kinetic energy. There is some motion relative to the center of mass. So the objects are moving relative to the center of mass, so there is some relative kinetic energy also. We'll find out what that is later on. We'll look at this whole thing from the perspective of the center of mass, but let's look at the initial and the final situation first, and then we'll take a look at the whole thing relative to the center of mass. Okay, there's one more thing I wanted to determine, and that is, what is the relative velocity? So what is VREL? And I want to determine that initially. We're looking at the initial situation. Remember, that is V2 initial minus V1 initial. So what is that? V2 initial is 3 meters per second minus V1 initial. V1 initial is 8 meters per second. So we've got 3 minus 8, what is that? Negative 5 meters per second. What is that telling us? Well, first of all, it's negative, so what does that mean? Negative means that the objects are coming together. Well, yeah, we would expect that before the collision. But they're coming together at 5 meters per second. Although M2 is going this way at 3, M1 is catching up because it's going faster. And it's catching up at a rate of 5 meters per second. That's what this VREL is telling us. It's telling us how rapidly they're coming together. Okay? Well, there we go. These are our initial results for the initial situation. Let's put some values in for the final situation and see how they all compare. What we found was the total initial momentum, and this is all initially before the collision, was 60 kilogram meters per second. The velocity of the center of mass initially was 6 meters per second. The total kinetic energy was 210 joules. The kinetic energy of the motion of the center of mass was 180 joules. And the relative velocity initially was minus 5 meters per second. So what happens after the collision? For an elastic collision, we would end up with a situation like this, assuming it's all in one dimension. We still have our 6 kilogram and 4 kilogram mass, but now the final velocity of the 6 kilogram mass is 4 meters per second, while the final velocity of the 4 kilogram mass is 9 meters per second. So what's happening? Notice, the mass 1 went from 8 to 4, while mass 2 went from 3 to 9. In other words, mass 1 is slowing down, mass 2 is speeding up. So what's happening is we're having a collision where they strike, and then mass 1 slows down, while mass 1 goes off faster. Physically, that makes sense. That kind of follows along with our common sense. So let's stick our numbers in here and see what we get. Let's calculate these things that we calculated initially. Let's calculate them finally. So the final momentum. What is the total final momentum? That's going to be the final momentum of mass 1 plus the final momentum of mass 2. So that's going to be 6 kilograms times 4 meters per second plus 4 kilograms times 9 meters per second, which leaves us with 6 times 4 is 24 kilogram meters per second, plus 4 times 9 is 36 kilogram meters per second. 24 plus 36, 60 kilogram meters per second. Well, what do we notice? We notice that the momentum is conserved. Our final total momentum is exactly the same as our initial total momentum. Okay, very good. What's the velocity of our center of mass? Well, remember, the velocity of the center of mass, finally, will be the total final momentum over the total mass. But since the total final momentum is the same as the total initial momentum, 60 kilogram meters per second divided by 10 kilograms, it is no surprise that we end up with the same velocity for the center of mass. So even after the collision, even after these things bang into each other, the center of mass is still moving at a constant rate. It's moving at the same speed after the collision, 6 meters per second, as it was before the collision. Okay, very good. What about the kinetic energy? What is the total final kinetic energy? Well, that's going to be the kinetic energy of the first mass plus the kinetic energy of the second mass. So that would be 1/2 times 6 kilograms times 4 meters per second squared plus 1/2 times 4 kilograms times 9 meters per second squared. And that's going to give us 1/2 times 6 times 4 squared gives us 48 kilogram meter squared per second squared, or joules, plus 1/2 times 4 times 9 squared is 162. 48 plus 62 is 210 joules. And what do we notice? Our final kinetic energy is exactly the same as our initial kinetic energy. That was the condition for this to be an elastic collision. An elastic collision implies that our initial kinetic energy must be the same as our final kinetic energy. The final momentum will equal the initial momentum for any collision, as long as the external forces are negligible. So this will be true even for collisions that are not elastic, but for elastic collisions, the kinetic energy is also conserved. What about this final energy of the center of mass? Well, since the center of mass is still moving at the same speed, we expect that to be the same. That will be the same. The kinetic energy of the center of mass, finally, which would be 1/2 times the total mass times the velocity of the center of mass, finally, which is exactly the same, we'll get exactly the same result we had last time, which is 180 joules. 180 joules. Okay, now what about the relative velocity? VREL. Remember, VREL finally. Well, that's going to be V2 final, V2 final, V2 final minus V1 final. V2 final is 9 meters per second, minus V1 final, which is 4 meters per second, which gives us a result of 5 meters per second, positive 5. Which is the opposite of VREL initial. So, what's happening here? Before the collision, the masses are approaching each other at a relative speed of 5 meters per second. After the collision, they're moving apart at 5 meters per second. So, negative relative velocity, positive relative velocity. Well, that makes sense. So, it certainly makes sense that our relative velocity is changing sign, but the fact is that for an elastic collision, they are exactly opposite each other. Okay, very, very good. Let's take a look at this from the position of our center of mass, or from the center of mass's frame, you might say. Well, now what is that? What does that mean? Well, remember the center of mass is moving at a positive 6 meters per second. What would this look like if we were moving along at 6 meters per second? In other words, imagine that I walk by this collision at 6 meters per second. What will that collision look like? Well, what we have to do is basically just subtract 6 meters per second from every velocity. Subtract it from VI initial, subtract it from V2 initial, subtract it from V1 final, subtract it from V2 final. And that will give us the velocities of the objects in the center of mass frame. In other words, what they would look like if we were moving along with the center of mass. Well, what are those values? Let's do that, and then we'll evaluate these quantities from the center of mass frame. Remember, we wrote that U was equal to the V minus the velocity of the center of mass. So we'll use U to represent the velocity as seen from the center of mass frame. So we're going to take all the velocities and subtract 6 meters per second. So U1 initial will be 8 minus 6, which is 2 meters per second. U2 initial will be 3 meters per second minus 6, which is negative 3 meters per second. Well, what does that mean? Well, if we are moving along with the center of mass, mass 1 will be moving to the right and mass 2 will be moving to the left. So from the center of mass frame, it looks like these two things are approaching each other this way rather than like this. So one's moving to the right, one's moving to the left. What about afterwards? Well, U1 final will be 4 minus 6, which is negative 2 meters per second, and U2 final will be 9 minus 6, or 3 meters per second. So what's happening here? In this case, we have mass 1 going in the negative direction, mass 2 going in the positive direction. So they are coming this way before the collision, and then going this way after the collision. Well, very interesting, very simple, very much simpler than perhaps we had before. Okay, so let's change our velocities to the values of u, and let's do these calculations for the momentum, motion of the center of mass, and kinetic energies and the relative velocity. Okay, let's take a look at that.